And then the other thing that's in the folder is balancing equations worksheet number 1. So this is practice about balancing chemical equations. Toward the top, there is some conceptual stuff about like what the concepts of balancing equations is all about. And then down toward the bottom, there's 3 examples. And then on the back, there's problems 4, 5, 6, 7, 8, 9, 10. So these are all chemical equations that are skeleton equations like we've already written. So you've got like names of like chemical compounds. They could be acids, they could be hydrocarbons, they could be diatomic elements, they could be covalent, they could be ionic. Basically, all the basic types of chemicals that you'll ever see in this course. And honestly, there really aren't too many other chemicals besides these, even in like AP physics or AP chemistry class. So the foundation for everything in inorganic chemistry, and even a little bit of stuff with some organic chemistry, you'll know how to do all that stuff with balancing chemical equations. One of the most fundamental things that we do in chemistry. And then we use that to help us understand like quantities and stuff. There's also this paper, this is reference sheet, steps to balance equations. And I didn't print this out, so you don't like have it here in class. But this has a thing about steps for balancing equations. And it's an extra example about how chemical equations can be balanced and kind of some mathematical ideas. And like next week, we'll do some practice with that. So anyway, in this balancing chemical equations notes, let me just go through a little bit of this real quick and show you some practical examples of what it means to balance equations. In the lab yesterday, you like saw about ratios of atoms. What's important in every chemical equation is that you've got reactants and then you have products. And the reactants and products are separated by the like yield sign. And altogether, this big overarching idea, the law of conservation of mass, says that you can't create or destroy matter in a chemical reaction. You've got so much mass of reactant and a certain mass of product. And the mass of the reactant and the mass of the product has to be the same. But further than that, you have to have the same number of atoms on both sides. So this whole idea of having like the same number of atoms on both sides of the reaction, that's what you did yesterday with the exercise with the like the M&Ms, is if you start out with like 4 red M&Ms that represent 4 oxygen atoms, when the reaction is complete, you still got to have those 4 red M&Ms for the 4 oxygen atoms. You can't get rid of or create new individual elements. So this procedure of what we call balancing chemical equations is to be able to figure out how many of each of the reactant and product chemical are necessary in order for the reaction to take place correctly. So this is one practical example. This is a beaker that contains bromine. Bromine on the periodic table is usually like blue for liquid, or it's listed as a liquid, but bromine has a very high vapor pressure. So in this beaker, the bromine is actually a brown liquid at the bottom, and then there's this brown vapor above it because it evaporates very easily. You don't have to know that necessarily, but bromine is one of only 2 liquids at room temperature, that and mercury. Any other liquid is a compound. And then there's some aluminum here. So if you take some aluminum and you dump it in with bromine, what happens in the reaction is the aluminum will react with the bromine until one or both of them is like used up. But the ratio of the number of atoms of aluminum to bromine in the reaction is determined by what the product ends up to be. So there's this compound that contains aluminum and bromine. So see, this is Al2Br6. This little diagram is not unlike the thing we did with like the M&Ms. This Al2Br6 compound, there's 2 aluminums. Those are like 2 yellow. So these yellow things are the aluminums. There's 2 of them. And then there are these 6 bromine atoms. And the 6 bromines kind of surround the 2 aluminums. So the compound itself is made out of 2 aluminums and 6 bromines. So there's 6 bromine atoms. And because the compound's made of two aluminum atoms and 6 bromine atoms, you've got to start out with that same number of atoms. Now, aluminum is just atomic. Aluminum atoms exist independently as single individual atoms. So if you're going to make this compound Al2Br6, you got to have two aluminum atoms. The compound's formula has a 2 after the Al. So that's kind of obvious, just two individual aluminum atoms. But bromine is one of those diatomics. It's one of those elements that always exists as two atoms bonded together. So because bromine is Br2, and altogether we need 6 bromines, you just need 3 of the bromine molecules. So altogether, it takes 2 aluminums and 3 bromine molecules, and you've got the correct constituents to make Al2Br6. If you're short any one of these individual atoms, the compound can't form. Like, if there's only 1 aluminum and 6 bromines, you don't even make the compound. You don't have the right stuff. You can't put it together. It's just not possible. So the ratio is important. Similarly, if you happen to have 3 aluminums, well, that third aluminum is just not going to take part in the reaction. It's not going to take part to form the product. So this process of what we call balancing the equations involves putting coefficients in front of each of the reactants and products until you've got the correct ratio. Now, although you could put a 1 here, we never put a 1 out in front. It's kind of redundant. It's like in an algebraic expression, you could write 3x plus y is equal to 7. That's the same as writing 3x plus 1y is equal to 7. But you know you don't write the 1. That's like dumb. It doesn't do anything because 1y and y mean the same thing. So you just don't write it. It's the same thing in balancing equations. This, like 1, we just don't write it. So in the end, the chemical equation is 2Al plus 3 bromines, Br2, yields Al2Br6. You can also account for the right number of atoms by counting them up on each side. On the left-hand side, there's 2 aluminums, and on the right-hand side, because it says Al2, there's 2 aluminums. And then, much like in an equation, like an algebraic equation, if you write 3 times 2x, that's the same as 6x. Here, because there's a 3 before the bromine and a 2 after, 3 times 2 gives you 6. So 3 times 2 is 6 bromines, and over here there's 6 bromines. So that all works out. That's a very basic example of a synthesis reaction where 2 different chemicals are forming this compound, and the compound is made up of a whole bunch of different atoms, and you just got to get the right number to start with. So that's the practical aspect to how like balancing equations goes. There's another way that you can see it. This is actually 3 separate slides in the slide deck, but I kind of put it all together into one. This is a skeleton equation. So this could be an equation that we've written from a written description. It could be, the written description would say magnesium reacts with oxygen to form magnesium oxide. So on the periodic table, magnesium is a metal that's not a diatomic, but oxygen is one of the diatomics. So in a written description, when it says oxygen, it's got to be O2. And then from the periodic table, you'll see that magnesium is in the second column, so it's Mg2+, and oxygen is in the 16th column, so it's O2-. And when magnesium and oxygen form a compound, because the charges are the same, 2+ and 2-, you only need one of each. So it's Mg plus O2 gives you MgO. A good thing to do is list which elements exist on both sides of the reaction. So a good process that a lot of people find helpful is just make a list of all the elements that appear on both sides. So here, I've got magnesium and I got oxygen. So you can list, I got magnesium, I got oxygen. On this side, there's magnesium and oxygen. And your goal is to demonstrate that there are the same number of atoms on both sides. So when you start out and you look at the reaction as a skeleton equation, there's 1 magnesium, but there's 2 oxygens as reactants. And then as products, there's 1 magnesium and 1 oxygen. So this equation is not balanced because it looks like 2 oxygens change into 1 oxygen. So that's just not right. Starting out, the magnesiums are balanced, 1 magnesium and 1 magnesium, but the oxygens are not, 2 oxygens and 1 oxygen. So in order to balance the equation, the only thing you can do is put coefficients in front of the individual reactants or products. So in order to start balancing this equation, what's unbalanced are the oxygens. But if you put a 2 in front of MgO, then instead of there being 1 magnesium and 1 oxygen, now there's 2 magnesiums and 2 oxygens. And it might seem like you did something wrong because at first the magnesiums were balanced, but now they're not. But that's completely okay, and it's a totally natural thing to have to do because many reactions have coefficients in front of a bunch of different things, and that comes about by going through the balancing process to keep putting coefficients in front of it, chemicals, so that you end up with the correct like total number of atoms on each side. So if I put a 2 in front of the MgO, now there's 2 magnesiums and 2 oxygens, and that unbalanced the magnesiums. So to fix that, if you put a 2 in front of the magnesium, then now there are 2 of each on both sides. There's 2 magnesiums on the left and 2 in front of magnesium on the right. And on the left, there's 2 oxygens, and now 2 times 1 is 2 oxygens. So this balanced equation tells you that to make the reaction go, you've got to take, for every 2 magnesium atoms, you need 1 oxygen molecule. And as a result of 2 magnesiums reacting with 1 oxygen, you get 2 magnesium oxides. So you never make magnesium oxide one at a time. You always make them 2 at a time. And you make them 2 at a time by taking 2 magnesium atoms and 1 oxygen molecule. If it were that oxygen was just monatomic, which it isn't, but if it was just Mg plus O making MgO, that would be a balanced equation. That would be good to go. But because oxygen is not monatomic, it's diatomic, that starts it off kind of like being a little bit messed up. All right, the one paper you have is, yeah, this thing, counting atoms and chemical formulas. So we can work through this example real quick. This is just counting up numbers of atoms in the compound. So for instance, chemical formulas can be written to show numbers of atoms. So you got like C5H12, there's 5 carbon atoms and 12 hydrogen atoms. This is pentane. So pentane is like single bonded carbons. It follows that rule CXH2X plus 2, because you've got 2 more than twice as many carbons, 2 more than twice as many hydrogens as you had carbons. Like 5 times 2 is 10 plus 2. Anyway, this is easy because it's just 5 hydrogens and 12 carbons. In these examples, sometimes they're easy and sometimes they're tricky. What matters is how to deal with the, what do you call it? The coefficients in front. So when you see NaCl, that's just 1 sodium. I wanted something else. There we go. 1 sodium and 1 chlorine. Mg3N2. Well, it's simple. 3 magnesiums and 2 nitrogens. If it's K3P, it's just 3 potassium and 1 phosphorus. If it's C10H16N5O13P3, that's a pretty large organic compound. It's just simply whatever number appears after the, let's see, oh, that's out of order. C10, N, there's 5, P, there's 3, hydrogen, 16, oxygen, 13. I think I got that right now. Yeah. Where things get a little tricky is how you deal with coefficients and how you deal with parentheses. So from simple to more complex, the NaNO3, that's sodium nitrate, there's only 1 sodium, there's 1 nitrogen, and there's 3 oxygen. But now when you have like 6 H2O, one way to understand this is when you put a 6 in front of the H2O, it means there's 6 water molecules. Each water molecule has 2 hydrogens. So the coefficient gets multiplied by however many of the individual atoms there are in the compound. So when you're dealing with hydrogen, it's 6 times 2, or 12 hydrogens. When you're dealing with oxygen, it's 6 times, there's only one of them, 6 oxygens. So there are 12 hydrogens, but 6 oxygens. 6 water molecules altogether are going to have 12 hydrogens and 6 oxygens available. The next one is the most complex thing you can see. So this is strontium nitrate, 2SR NO3 2. You got a coefficient, you got a parenthesis, and then you got a number after it. So one way to deal with this is you can just deal with the compound itself. Don't worry about the coefficient out in front. In the compound itself, there's one strontium. So there's like one strontium atom. Because the nitrite is inside a parenthesis with a 2 outside it, this 2 on the outside of the parenthesis tells you that there are 2 nitrites. Every nitrite has only 1 nitrogen. So because there's 1 nitrogen inside the parenthesis, but there's a 2 on the outside, there's 2 nitrogen atoms in just the compound itself. Inside the parentheses, there's also an O3. So every nitrite has 3 oxygens, but there's a 2 outside it. And 2 times 3 is 6. So this compound has 6 oxygens. Just the compound itself, ignoring the coefficient in front, is made up of 1 strontium, 2 nitrogens, and 6 oxygens. But now when you consider this coefficient out front, so there's 2 of the compound, that doubles all the numbers of atoms themselves. So all together, in this expression of 2SR NO3 2, there are 2 strontiums, 4 nitrogens, and 12 oxygens. Another way to look at it is the number of atoms is the product of the coefficient, the subscript, and what's outside the parenthesis. So for strontium, the only thing that there is a coefficient, so it's just 2. For the nitrogen, it's the product by multiplying the coefficient, the subscript, and the parenthesis. The coefficient is 1, or the coefficient is 2, the subscript is 1, and outside the parenthesis there's a 2. So it's like 2 times 1 times 2, that gives you 4. For the oxygen, there's a coefficient, subscript, and the parenthesis. So there's a 2 for a coefficient, there's the 3 for the subscript, and the 2 outside the parenthesis. So it's 2 times 3 times 2. It gets you 12. So every strontium nitrite has 1 strontium, 2 nitrogens, and 6 oxygens. But when you have 2 of them, it's 2, 4, and 12. So like 2, 4, and 12. Another thing that you see is in some compounds, the same element appears more than once. So this 4, NH4NO3, that's ammonium nitrite. I'll write that over here. 4 NH4NO3. So first off, you might say, well, why is there nitrogen in 2 different places? Why don't you like put them together? You know, wouldn't it be nicer if you just write like N2H4O3 or something like that? That way the nitrogens are like together as 2. But you see, this is an ionic compound. When you look on the ion chart, you'll find ammonium, that's NH4, and you'll find nitrite, and that's NO3. There's another kind of thing that's going on here, and that's whenever it's an ionic compound, we write the anion or the cation and the anion beside each other, and this could be a different compound than this. It turns out this is actually, a nitrogen complex. So it's a formula for a compound that has the same formula, but it's not an ionic compound. But the thing to know here is when you're making a list of the numbers of atoms, The compound itself, so just repeating again, in the compound, there's a nitrogen here and a nitrogen here. So that's 2 nitrogens. There's 4 hydrogens. And then there's 4 hydrogens. And then there's 3 oxygens. So in the compound, just the compound itself, 2 nitrogens, 4 hydrogens, and 3 oxygens. But because there's a 4 out in front, that there are 4 ammonium nitrites, the 4 gets multiplied by all these numbers. So in the expression 4 NH4NO3, there's a total of 8 nitrogens, 16 hydrogens, and 12 oxygens. That's the total number of atoms altogether. So being able to count the number of atoms is really important. There aren't like little spaces on there because that paper got like messed up, I think. See what it looks like on there. Yeah, but there's that little hole. Okay, other ones, if you have 6 of the pentanes, 6 times 5 is 30, and 6 times 12 is 72. So you can see that if you have large organics like pentane, you got 6 of those, you can end up with a whole bunch of individual atoms. I don't know, other things to do in this practice, Na2CO3, how many sodiums? There are 2 sodiums, this is in the bottom center. How many carbons? There's 1 carbon, and then there's 3 oxygens. But then if you have 2 Na2CO3, the 2 out in front just doubles. So now there are 4 sodiums, 2 carbons, and 6 oxygens. Anyway, so that's the basic plan. Let's do this. So here are some examples of things to do. Ooh, that got messed up. Okay. On the, well, I don't know, you can write this on the back of there, or if you have a separate paper in your notes or something like that, we'll do each of these. I'll just show you a couple, and then just kind of have you do it at the same time and see what we kind of end up with. None of these compounds are anything that you haven't seen or know how to write before. There are no states included because the states don't matter, like whether it's solid, liquid, gas, or aqueous. That doesn't matter with balancing equations. What matters is by comparing the subscripts and stuff like that. So there's a couple different methods. Sometimes they're easy, like this Na plus Cl2 gives you NaCl. One method to do is to make a list of reactants and products and the numbers of atoms on each side. So, oops. You can write Na and Cl. Those are the 2 atoms. And I've got reactants and products. So if you just make a list of how many atoms in reactant and product for each of the chemicals, that's a starting point. What I mean by that is make a list from what the equation shows you, how many atoms of each there are. So I got 1 sodium and 2 chlorines. Those are my reactants. And as products, there's only 1 sodium and 1 chlorine. So it's unbalanced because on the left-hand side, there's 2 chlorines, but only 1 chlorine on the right. So the only way to fix that is to put a coefficient in front of one of the chemicals. So you see, if I put a 2 in front of the NaCl on the right-hand side, what that does is it doubles the number of sodiums and the number of chlorines. So now instead of there being 1 sodium and 1 chlorine, now there's 2 sodiums and 2 chlorines. So you fix the chlorine problem, but you created a problem with the sodium. But there's an easy fix to that. You slap a 2 in front of the sodium. And now you got 2 sodiums on the left, 2 sodiums on the right, 2 chlorines on the left, and 2 chlorines on the right. It won't always be that they're the same numbers of each. That's just kind of coincidental here. But the other way to read that is to make that reaction go, you've got to have 2 sodiums for every chlorine. Just the same as like putting ingredients together for cooking food, or putting things together to make stuff happen. There's certain proportions you gotta start out with. All right, number 2 is the combustion of methane. If we use the burners here in the room, or you have a natural gas stove or a natural gas furnace in your home, this is the reaction. It's methane and oxygen makes CO2 and H2O. So you can make a list of the atoms if you want. We've got carbon, hydrogen, and oxygen. So starting with the reactants, there's 1 carbon, there's 4 hydrogens, and there's 2 oxygens. So in my little list here, I got carbon, hydrogen, oxygen. This is the number of reactant atoms: 1 carbon, 4 hydrogen, 2 oxygen. For products, I got 1 carbon, 2 hydrogens, and 3 oxygens. Because there's 2 oxygens in the CO2 and 1 oxygen in the H2O. So you got a choice of what you want to do. You can either try to fix the hydrogens, or you can try to fix the oxygens. It doesn't make a difference which one you do first. But you're looking for the least common multiple of the numbers. Because oxygen, there's a 2 and a 3. You can't just multiply this by something to get that. You can't multiply this to get that. The least common multiple is 6. So the hydrogen might be a smarter one to start with. Because there's 4 hydrogen reactants and 2 hydrogen products, if you put a 2 in front of the H2O, that now doubles the number of hydrogens. So now you've got 4 hydrogens, but then on the right-hand side, now you got 4 oxygens. Because you see, when you put a 2 in front of the H2O, now in your list of atoms, now there's 4 hydrogens, and there's 2 oxygens here, but 2 more there. So now you got, you fix, the carbons are still okay. You fix the hydrogens, now the oxygens are in bad shape. So because there's 2 atoms of oxygen as reactant, but 4 atoms of oxygen as product, you need to double the number of oxygens as reactants. So if you put a 2 in front of that H2O, now you got 4 of oxygen. Another way, that a lot of people just do it, and how I do it is, you can just go 1 atom at a time. So what I mean by that is, I'll just rewrite the reaction. If I just write CH4 plus O2 gives you CO2 plus H2O. A quicker way sometimes is to examine each individual atom. So what I mean by that is, you start with the first thing on the left. There's 1 carbon on the left. And when you look on the right, there's 1 carbon on the right. So it looks like carbon's okay. The next element is hydrogen. And on the left side of the equation, there's 4 hydrogens. But on the right side of the equation, there's only 2. So the hydrogens are wrong. And you can fix that hydrogen. And so without making this list, you can just say, well, if I put a 2 in front of this hydrogen, now my carbons are okay. 1 carbon on the left, 1 carbon on the right. 4 hydrogens on the left and 4 hydrogens on the right. The next element is oxygen. There's 2 oxygens on the left. And when you look on the right, I've got 2 here in the CO2 and 2 here for the water. So that's 4 oxygens. And you can go back and put a 4. But I will tell you that once you get to this last atom, you got to go back through and double check everything, because what can happen is when you put a number in front of a compound, it can affect like more than one element in the compound. So even though you think it might be done, I'll go back and be like, okay, I got 1 carbon on the left, 1 carbon on the right. There's 4 hydrogens here and 4 hydrogens here. And then on the left, now there's 8 oxygens. Oh, I didn't mean to put a 4 there. Holy crap. Just a 2, because I want 4 altogether. 4 oxygens, and now on the right, there's 2 oxygens here and 2 oxygens there. So that's 4. I never meant to write a 4. I was just thinking 4, so I wrote a 4. Or I said the word 4. All right, write down number 3 and 4. Try those. And this is actually the same thing that you did with the M&Ms. Like each M&M represented an individual atom as a reactant or product. All right, so number 3 is lithium reacts with nitric acid to make lithium nitrate and hydrogen gas. That's a reaction that happens. You put lithium into nitric acid. Well, you get two things because nitric acid also has water present, and nitrogen reacts with the water. But if you make a list of the number of atoms of each of the elements, it looks like this one's going to be quick and easy to do because you're like, okay, I got one lithium on both sides. That's hot. I got one nitrogen on both sides. That's good. I got 3 oxygens on both sides. Only thing I need to do is fix the hydrogen. So that's going to be quick and easy. You stick a 2 in front of the hydrogen on the left. So you see that there are 2 hydrogens on the right, but only 1 hydrogen on the left. You put a 2 here, and you're like, okay, now I'm done. Except you're not done. You went from having 1 element that's messed up to now having 2 elements that are messed up. Because when you put the 2 in front of the nitric acid, it doubles the number of hydrogens, it doubles the number of nitrogens, and it doubles the number of oxygens. So don't think you went down the wrong road, because you never will, in a way. By putting the 2 in front of the nitric acid, you've doubled the number of hydrogens and made the hydrogens right, and it messed up the nitrogen and oxygen. But don't let that worry you, because so now we got to fix the nitrogens if you want. And to fix the nitrogens, we're going to have to double the number of nitrogens on the right-hand side. So, because on the left here, you got 2 nitrogens, and on the right-hand side, there's only 1 nitrogen. So if you put a 2 in front of the lithium nitrate, well, now that doubles the number of nitrogens. So now there's 2 nitrogens, but now there's also 2 lithiums. Now there's 6 oxygens. So what has happened is you've sort of like accidentally fixed the oxygens in a way. The oxygens were wrong. They were 6 and 3. Now they're 6 and 6. That's nice. Nitrogen's 2 and 2. Hydrogen is 2 and 2. But now the lithium's screwed up. So to fix the lithium, just kind of slap a 2 in front of the lithium. There's another way to do this one. And that's like this. You see how there's this NO3? That's the nitrate. There's also an NO3 over here. That's a nitrate. No matter what, you need to have the same ratio of the nitrates on both sides. So when I look at this reaction, instead of looking at, and this is another way to deal with it, instead of looking at it as lithium, hydrogen, nitrogen, and oxygen, you can also balance it as numbers of lithium, hydrogen, and nitrate. Because no matter what coefficients you put in front of the nitric acid and lithium nitrate, the NO3 is always like a ratio of 1 nitrogen to 3, 1 nitrogen to 3 oxygen. So if you balance it as lithiums and nitrates, now you see there's like 2 lithiums on the left, 2 lithiums on the right. I got 2 hydrogens on the left, 2 hydrogens on the right, but there's also 2 nitrates and 2 nitrates. So that's another way to visually see it, is that the NO3 remains like together as a group. All right, and you can double check it. So to double check, you get 2 lithiums on the left, 2 lithiums on the right, 2 hydrogens on the left, 2 hydrogens on the right, 2 nitrogens on the left, 2 nitrogens on the right, and 2 times 6 oxygens on the left, 2 times 3 is 6 oxygens on the right. So the Al plus oxygen makes aluminum oxide. So aluminum is a nice, bright, shiny metal. Exposed to oxygen, it gets a little coating that's kind of a grayish color, like a whitish gray instead of being like shiny. When you make a list of the number of atoms, you got one aluminum on the left and two aluminums on the right. So in my little list here, I got one aluminum on the left, two on the right. Oxygen is two on the left and one on the right. It makes no difference which one you start with. But as you get good at this, you'll see which one is the right one to start with. If you start with aluminum, and this is a thing where you might have to chase them around a little bit, because you start with one aluminum on the left and only two on the right, you need to double the number of aluminums. If you put a 2 in front of the aluminum, now the aluminums are balanced, but the oxygens are wrong. A little trick is if the coefficients aren't divisible into each other, in other words, like if it's not 2 and 4, but it's something like 2 and 3, you need to find the least common multiple of the coefficients, and that's 6. So you're going to need to have 6 oxygens on both sides. So what you have to do to have 6 oxygens on both sides is you got to put a 3 in front of this oxygen on the left and a 2 in front of the aluminum oxide on the right. The problem is when you put the 3 in front of the oxygen, now you got 6 oxygens on the left and 6 on the right. But when you put the 2 in front of the aluminum oxide, now that changes the aluminums to 4. So the aluminum switched to 4, and then the right-hand side, the 2 wasn't correct in the first place. So you'd have to cross that out or erase that, and it's got to be a 4. So it turns out you need 4 aluminums with 3 oxygen molecules, and that makes 2 aluminum oxides. There's no other ratio that works. So it's going to be 4, 3, and 2. The more you do, the better you get. And you're going to be balancing equations most days in this course. That's like one of the fundamental things you got to always do. There's no getting around it. See, when you take a written description of a reaction, like aluminum reacts to oxygen to make aluminum oxide, you got to write the formulas. When you write the equation, then you find out that it's not balanced and you have to balance it. But the written descriptions of equations never include ratios with coefficients. You got to come up with those as you go. All right, in gasoline, there's a molecule called octane. Octane is C8H18. It reacts with oxygen to make H2O and CO2. I'll make a list: C, H, and O. On the left-hand side, there's 8 carbons. On the left-hand side, there's 18 oxygens. And on the left-hand side, there's 18 hydrogens and 2 oxygens. On the right-hand side, there's 1 carbon, 2 hydrogens, and then 3 oxygens. 3 oxygens because there's an oxygen in the water and 2 oxygens in the CO2. So these numbers don't look nice and neat at all. And it sort of doesn't matter which one you start with. But if you're just going atom by atom, on the left-hand side, there's 8 carbons. And on the right-hand side, there's only 1 carbon. And in our little list here, we definitely need more carbons. So if you stick an 8 in front of that CO2, now that changes the number of carbons to 8. And it changes the number of oxygens to 17. 17 is a horrible number. Because the least common multiple of 17 and 2 is 34, which is not fun. So it doesn't matter which atom you do next. You can do hydrogen if you want. So you see there's 18, like carbons are balanced at this point. There's 18 hydrogens on the left. There's only 2 on the right. So if we stick a 9 in front of here, that changes the number of hydrogens to 18, but it's also changed our number of oxygens. There were 16 oxygens here, and then here there are 9. And 9 and 16 comes out to be 25. So now the deal is the oxygens are unbalanced. The hydrogens are good, the carbons are good, but the oxygens are not. And the least common multiple of 2 and 25 is 50. That's it. It's just the product of 2 and 50, or 2 and 25. So to get 50 on both sides, you got to multiply the oxygens by 25. There's going to be a 25 here. But you also got to multiply all the things on the right by 2. So this comes out to be a 2 here. This has got to change to 18. And this changes to 16. So then all together, there's 16 carbons on both sides. There's 36 hydrogens on both sides. And there are 50 oxygens on both sides. But here's a thing I'll say about this. What this reaction shows you is that when you want to drive a car down a road using gasoline with octane, these numbers out in front, they tell you how many of each kind of molecule you need. In order to make this reaction go, you need a total of 27 molecules. You only have to buy 2 of them. The other 25 are free. You buy these 2 at the gas station. These 25, you're running into them as you're driving the car down the road. So this ratio of atoms or molecules tells you how it all has to go. So in a gasoline engine, as the engine's running, for every 2 molecules of octane that comes from the gasoline, the car's also got to take in 25 molecules of oxygen. But those are free. That's pretty hot. It's nice you don't have to buy the oxygen too, because then that would be a lot more money. All right, the rusting of iron, this one comes out to be, you got to have a 2 in front of the iron oxide, a 3 in front of the oxygen, and a 6 in front of the, or a 4 in front of the iron. So there's 4 irons, 6 oxygens on both sides. Okay, so the other paper I gave you, that has more to practice. Practice those